Welcome to the Automation World Get Your Questions Answered podcast, where we connect with industry experts to get the answers you need about industrial automation technologies. I'm David Greenfield, Editor-in-Chief at Automation World, and the question we'll be answering in this episode is, what are LiDAR sensors? And joining me to answer this question is Aaron Rothmeyer, Product Manager for Dynamic Ranging Products at SICK, a supplier of sensors, safety, machine vision, and networking technologies and services. So thanks for joining me today, Aaron.
Absolutely. Yeah. Happy to be here, David. Thank you.
So, Aaron, let's just start by explaining what LiDAR sensors are and how they differ from other position detection sensors commonly used in manufacturing, like proximity, position, or vision sensors.
Sure. Yeah. It's a very good question. And it's a question I'm happy to answer because, we hear a lot about LiDAR and it seems like a very complex technology, but in reality, it's quite simple. It's just purely a sensor that's designed to do distance and ranging, as is implied in the name, which LiDAR is basically an acronym for light-based detection and ranging. And as it implies, you're using lasers or light to basically do detection of objects or do ranging. And that's based off of the time of flight principle, where in the LiDAR sensor, we're sending out a bunch of pulses of laser light. We can calculate the amount of time it takes for those laser pulses to get out and back. And then based on the speed of light, we can figure out exactly how far it is to a target. So it's a very simple technology when you sit down and look at it that way. But there's certainly benefits of using this type of technology versus, say, basic proximity or position sensors. One of the big ones is range. Since we're using lasers, obviously lasers have a very long range typically. So where a typical proximity sensor might max out at around 1 meter or so, with a LiDAR sensor, often we can get much, much, much farther. 80 meters, 100 meters is no problem at all, depending on a variety of factors. But these are much longer range sensors. And then resolution is typically outstanding as well. Even at those longer ranges, in the tens of meters, we can often get very good resolution, sub-centimeter or even sub-millimeter resolution, depending on the technology. So while often there's a trade-off between range and resolution, with LiDAR, oftentimes we can get both. We get the best of both. We get very high resolution, even at longer ranges. And then the biggest ones on top of those two are, ambient effects. If there's weather, anything like that. If you're using a camera, or if you're using, certain technologies that aren't really meant for outdoor use, you might end up with issues if there's rain, snow, heavy sunlight, stuff like that. LiDAR is typically fairly immune to those effects. And then field of view, where with a traditional proximity sensor or industrial capacitive sensor or anything like that, you're going to end up with issues with field of view. You're very limited. It's just a single point of detection. With both 2D and 3D technologies with LiDAR, you get a much larger field of view. Could be 360 degrees, depending on the technology. So you can get a lot out of a LiDAR sensor.
So you said these were simple sensors, and I understand that, but they can do quite a bit. So that's very interesting. Thanks for explaining the expansive capacity of LiDAR sensors compared to more of the standard sensors used in manufacturing. And you mentioned about how LiDAR sensors can generate 2D and 3D images. How do they do that? And what is that kind of data used for?
Yeah, good question. And I would say that the technology varies pretty greatly between different sensors. There's a lot of ways to do this. But with 2D sensors, primarily, in most cases, it's just a spinning motor. And that spinning motor rotates a mirror, and we bounce a laser off of that mirror. And so as the motor rotates, we're basically sweeping a laser to generate this range or this large field of view of laser distances. That's primarily how it ends up getting done with two-dimensional sensors. With three-dimensional sensors, now when we say 3D, we're not just doing left to right or an X, Y. We're actually going vertically as well. And when you go vertically, well, there's got to be another way to generate that. And that right now is a very hot topic. What's the best way to do that? If it is, a mechanical system where there's some type of movement inside the sensor to generate that vertical field of view, it's often done by basically spinning a large number of lasers. So instead of just taking one laser and rotating it, we take advantage of a technology called VCSELs, which is a surface emitting laser, to basically create a large cloud of lasers and then spin them. And that's one of the more popular ways to do it right now, but there's certainly other people working on other technologies as well, such as solid state LiDAR, where a variety of technologies are being employed to basically create a much larger cloud of measurement points.
One of the most common applications for LiDAR sensors that I've seen anyways is around their use on autonomous mobile robots. Can you explain why the use of LiDAR is so prevalent on AMRs?
Sure. Yeah, but I will say, first of all, LiDAR is a great technology. It's not the only technology that's used on, AMRs, for example. Many times when you look at an AMR, you'll see a LiDAR sensor on there. You're right. It's very prevalent. But you'll also often see other technologies next to it. And I think that's an important point to make because, we can't say you can just throw a LiDAR on any system and make it, reliable and safe. And that is the goal, is if you got an autonomous vehicle traveling through a facility, it has to be reliable to maintain uptime, and it has to be safe so that nobody's getting injured by this technology. And in order to make that happen, oftentimes engineers have to use multiple types of sensing in order to make it reliable and safe. And so LiDAR has a lot of good things going for it. You often see it next to a camera or maybe a radar to supply some multimodal sensing technology. But I think it's mostly popular in all AMRs because it has that large field of view. If you think about a camera, or you think about a radar, or you think about ultrasonic sensors or something like that, the field of view is typically quite limited. With a LiDAR, however, if you've got a spot, right on top of the machine that you can mount one of these, and you can take advantage of that full 360 degrees, you can really cover a lot of area around the AMR as it's traveling with one sensor. And I think that's a pretty important distinction between other technologies. But also, it's also an active sensor, right? So because we are sending out our own laser light, we're not dependent on, say, ambient light. So you hear a lot of buzz about, lights out facilities and stuff like that. Even if it's not a lights out facility, lighting changes as you travel through a warehouse, right? People open up garage doors, dock doors, windows get open, things change. Sun travels from, east to west. There's all kinds of things going in through the windows. And so if you're relying on a technology that uses ambient light, that can create issues with your reliability of your system. With LiDAR, we're sending out our own pulses of light. We're capturing them when they come back. It's very, very immune to any kind of ambient light issues or just other things that change in the environment, like dust entering the air or, sawdust getting kicked up. Anything that's going on there is quite immune to those types of effects. And that makes for a more reliable system. It also, because we're sending out our own light, we can really deal with really nasty targets as well. So certain targets that are, say, dark or glossy or dirty, they're going to interact with light differently. And so if we're just relying on ambient light, that can lead to issues. But we're sending out our own light, and it can be nice and high intensity and of a very precise wavelength. So when we hit something like, say, forklift forks, which is a very common target that we hear about a lot from our manufacturers and our end users, if we're trying to detect something dark like forklift forks, that's a pretty reliable detection for us. Because as we send out a pulse of high intensity light, it bounces off that dark target, we receive it back. It's easy for us to detect it. With a camera or other technologies, maybe not so much. So that's, I think, one of the reasons it's so prevalent, and you see it on nearly every AMR.
Yeah, thanks for explaining that. I did not realize that about LiDAR, about its the precision in different lighting environments. Makes sense when you think about it, especially as you mentioned with AMRs, but that's something that I hadn't really realized was a key differentiator in the technology before. Now, I noticed you mentioned in your answer there about using that to detect the forks on a forklift, being dark in different areas of a factory as well, and LiDAR being able to detect that. Are there other applications in the manufacturing industries for LiDAR beyond AMRs or, as you mentioned, the detection of the forklift forks?
Oh yeah, for sure. We are like we talked about, we are quite successful on AMRs. But outside of that, we spend a lot of time. We're an industrial company at SICK. We've been around for 75 years in the industrial space, and spend a lot of time making sure that these other applications within any kind of warehouse or industrial manufacturing facility are also seeing the benefits of LiDAR. And so some of the ones that we've seen for sure are in quality control, guidance of a traditional industrial robotic arm, inventory management, and just general process optimization where you're doing volumetric calculations of maybe a load on a pallet or something like that. You want to make sure that the load on the pallet is properly sized before it leaves your facility or something like that. Outside of that, the range and the field of view leads to some really good applications that aren't typically solved by other technologies. For example, crane anti-collision. If you've got a large gantry crane overhead, typically, as these cranes travel back and forth, they've got a pretty good understanding of where they are using various technologies, but determining where the actual hook of the crane is as it travels through the facility is difficult to predict. But using LiDAR, using the large field of view, we can look down and basically make sure that crane hook, as it's traveling through the facility, isn't going to collide with racking or any other cranes or anything like that as it goes through the facility. That's a big one. And ASRS systems, automated storage and retrieval as well. We're seeing a lot of people look at those types of systems with LiDAR to make sure that as those vehicles travel through those narrow aisles, they're not colliding with stuff that's hanging out of the racks. One of our favorite stories is a user that stores frozen turkeys, right, in a large cold storage freezer. And as the ASRS system goes back and forth, if these pallets of turkeys are hanging out the aisle and the collision occurs, well, it's a very large mess, creating a lot of downtime that everybody wants to avoid. So using LiDAR, we can look right down that aisle, and as the vehicle travels, if there's anything hanging off of the rack, we can make sure we don't have turkeys on the floor.
Yeah.
So,
You don't need turkeys on the floor, that's for sure.
yeah.
Aaron, one thing you mentioned there in your explanation of the other applications for LiDAR, you mentioned quality control. Can you explain that a little bit about how it's used there? Because I'm usually used to seeing, vision sensors using that. Is LiDAR more for like presence absence type detection, or is it something different?
Yeah, vision systems are outstanding at that, and we're a 3D vision manufacturer as well. We do a lot of cool stuff with 3D vision, but quality control has a wide definition, right? Quality control can get into some very large objects as well, and if we want to say create a digital twin of an object and then verify that the produced object matches that digital twin, we can do that with LiDAR. LiDAR versus 3D vision, a lot of times if you're looking at a 3D vision system, it's going to be very high resolution, sub-millimeter. Whereas often with LiDAR, you're going to end up with something more like sub-centimeter as far as your resolution and your accuracy goes. And so you got to pick and choose which one is the best one for that object. If it is a very large object, if you're trying to say look at a vehicle body and determine that vehicle body is formed correctly, or even a train car, for example, you want to make sure the train car is formed correctly. That's probably something that you could accomplish with LiDAR, where it would be difficult to get that field of view and that range out of something like a 3D vision system. Okay. So just a question of what your object is and how precise your tolerances are.
Okay, understood. Thanks for explaining that, Aaron. So how do LiDAR sensors compare in terms of cost to other more standard position and detection sensors?
Yeah, that's a very insightful question, David. And to be quite honest, it's typically higher. It depends, on the exact technology you're comparing to, but LiDAR traditionally has been a higher cost solution. And I say traditionally because, there's a couple things to keep in mind here. One is that because of the range and field of view of LiDAR, often you can replace several sensors. You kind of have to think about it from a system standpoint. If you are able to replace, say 100 traditional proximity sensors with one LiDAR, well, that can still be a cost saving. You got to keep in mind, you can do a lot with LiDAR, right? The other thing is just, having done this, I've been watching LiDAR for the last 20 years roughly. And in that time, in those 2 decades, the cost has dropped dramatically, by an order of magnitude. Most LiDAR sensors used to be in the 5 figures at least, as far as, just one sensor goes. And since then, we've seen certainly drop into 4 figures. And in many cases now, we're able to get LiDAR sensors on the order of several $100s for a single sensor. And so that cost, while still high, is definitely dropping dramatically. And I really look forward to seeing where it goes, in the next decade or 2.
So with that higher cost, that's, of LiDAR sensors versus standard sensors, how can a manufacturer determine if the use of a LiDAR sensor in an application is the right way to go versus the use of a more standard position sensor?
Good question. Yeah, and this, again, we've got to look at it from a system standpoint, and it all comes down to really the requirements of that particular application. In most cases, if a manufacturer is looking at a sensor suite for whatever application that they have, if we know that they are looking for something with a longer range, for example, or a larger field of view, they need to see 360 degrees around a vehicle, for example, or they need to see several tens of meters out, or they know that it's going to be a particularly difficult environment. For example, they know there's going to be a large amount of dust in the environment, or there's going to be no ambient light or very high ambient light, or it's going to be a very difficult application. Well, then LiDAR might be a good sensor to consider if it needs longer ranges or higher fields of view, or if there's any kind of precipitation or fog or anything like that in the atmosphere. It might be something worth taking a look at LiDAR for.
Now, I know you've given a few examples of LiDAR use beyond AMRs here in our discussion today, Aaron. But since we're talking about application examples and determining, if LiDAR makes sense, can you provide an example or two of manufacturers using LiDAR in production operations and why they chose to use LiDAR in those applications?
Well, sure, yeah. Well, the first one may seem obvious at first, but I do want to point out that, we stand behind our own products. We use our own products. We're an industrial manufacturer of automation equipment as well. And SICK in particular uses our products, our LiDAR products, in our own manufacturing processes. So one example of where we do that is in an application that's called pick wall. So in a lot of warehouse facilities and also just in light manufacturing facilities, you'll have what's called a pick wall, where it's a series of bins, could be, tens of meters long, could be just a bench top. Either way, it's just a series of bins. And as the operator is working at that wall, they're reaching into these bins and pulling out various components, right? It could be O-rings, it could be bolts, it could be T-shirts, it could be anything. But they're reaching into these bins and they're picking out objects. And the part of the control process wants to know how many times has the operator reached into this bin, or reached into that bin, or reached into that bin. And it's an application that's been around for years, and it's been solved in a variety of ways. But with SICK, we use one of our LiDAR products called the TIM to basically monitor. We're creating it's a 2D sensor, so we're just creating a vertical wall in front of the pick wall. And as the operator reaches through the plane of our LiDAR, it's detecting where that happened. It basically translates, the reach into the bin into a XY Cartesian coordinate that says, okay, the operator reached into this bin. And so now that our process control system can look at that and say, okay, operator reached into that bin, go ahead and move on to the next step. And then reach into, over here, into the other bin. And it works very reliably with our process. And it allows us to verify that the operator is doing things correctly with a single sensor. You don't need to have, a wide variety of sensors all wired up across this wall. Just one sensor can do it all. And so that was a big value to us. not having to wire up, 100 different sensors for a single wall. But we also have other manufacturers out there, such as Omron. Omron is a customer of ours for a long time, who's been using 2D sensors on their AMRs, on the AGVs that run around, coming from the Omron facility. And those have been using LiDAR sensors for a long time, basically to detect small objects. One particular use case that we ran across was on top of these AMRs. When they start up, they want to verify that nothing is around the AMR so that it can start moving in the direction it needs to move. And that object, those objects could be quite small. They could be cables. They could be wire racking, stuff like that, very difficult to detect. And so they needed a sensor with a high resolution to pick up those types of small objects, even right on startup. And the LiDAR sensors are able to do that quite readily. So there's a lot of reasons that people use, LiDAR in those types of applications, but those are a couple that we have for you.
Well, thank you again for joining me for this podcast, Aaron. And thanks, of course, to all our listeners. And please keep watching this space for more installments of Automation World. Get your questions answered. And remember, you can find us online at automationworld.com to stay on top of the latest industrial automation technology insights, trends, and news.